Yeah.
A very good afternoon to all the esteemed gathering here for second week of teacher enrichment workshop entitled as Differential Equation and Mathematical Modeling in collaboration with the National Center of Mathematics, Joint Center of IIT Bombay and TIFR. I would like to request all the participants to please keep your mic at the mute mode. And now in continuation of yesterday's lecture, now I request Professor Rashmi Bhardwaj ma'am to please start the session.
Yeah, thank you. Today, I will try to cover whatever be the assigned to me and then go to the modeling section.
Thank you,
And
ma'am.
I tried to keep some programs also because yesterday you asked about that. So I kept for all those things, the programs also. And I think you try it in a MATLAB program and it is easy to that because I have write down all the steps how to perform that. Okay. So I'm starting the presentation and I try to keep the simple way because sometimes mathematics will not keep so interesting. So I try to keep the pictures and combination of that. Anyway, uh, is it visible?
Yes, ma'am.
Okay, today I will try to cover the stability theory, Lipno characteristics, exponent and bifurcation and the manifolds, and then I will take the different examples on the human body movement as well as on the nanofluidics. No? So basically I try to give this because everyone afraid with the mathematics. Here we have the gathering of mathematicians, but normally people ask why you study the mathematics and what is the use of that. So I simply want to say that mathematics is not only a theory, it is a combination of an art, language, process of thinking, and now practicals, because the complete computer is nothing but it is based on the mathematical models. And a simple way to explain what is mathematics, we all see our hands, and we have the all the function in our hand. You see that this is known as our lifeline, which is nothing but a y equal to x. This is our heart line, which is y equal to exponential x. And this is our luck line, which is equal to y equal to log x. So this is a headline, means our IQ level increases, and this is our luck line. So this is not as such, it varies as a logarithmic function. And but if you combine both, that remains to be our life, which is a linear function y equal to x. So in a simple way, if we try to find out our functions or our things near to our surroundings, I think we can love the mathematics. Anyway, this is just to give the glimpses that yes, everywhere we have a mathematics. Now we come to the stability theory. Yesterday we discussed a lot about that, but basically a linear time invariant system is stable if the natural responses approaches to zero as time approaches to infinity. Linear time invariant system is unstable if the natural response grows without bound as time approaches to infinity. Also, the linear time invariant system is marginally stable if the natural responses neither decays nor grows but remains constant or oscillate as time approaches to infinity. Yesterday, I gave the example of the iteration processes where I showed by taking the example of simple x square plus c, and then how as c varies, you are getting the different type of the structures. So in order to know the location of the poles, we need to find the roots of the closed loop characteristic equation, which we used yesterday also. It turned out, however, that in order to judge a system's stability, we don't need to know the actual location of the poles, but we just need their sign only. That is whether the pole are in the right half plane or the left half plane. So this is the most important criteria which is given by Harvey's, which can be used to indicate that a characteristic polynomial with negative or missing coefficient is unstable. So the Rao-Hurwitz criteria is called a necessary and sufficient test of stability, because a polynomial that satisfies the criteria is guaranteed to stability. And the criteria tells us how many poles are in the right half plane or on the imaginary axis. Now, simply I'm taking the Rao-Hurwitz stability criteria. It is a method for determining continuous system stability. It states that the number of roots of the characteristic equation with positive real parts is equal to the number of changes in sign of the first column of the Raoult theorem. So this is very important theorem, which says that whatever be the characteristic equation, how many positive real parts, which is equal to the change in the signs of the. Now you see that what is that, and this method yields stability information without the need to solve for the closed loop system poles. Using this method, we can tell how many closed loop system poles are in the left half plane or in the right half plane or on the axis itself. And we generate the route table to see that the characteristic equation of the nth order continuous system, which can be written as this one, where an Sn plus an minus 1, we know that how we have to write down the polynomial. Now we are using the stability criteria. Route table is an. You leave the an minus 1, means you have to make an, then an minus 2, an minus 4, means you are taking a 2 separately, which is with a Sn coefficient. Then you are writing as an minus 1, an minus 3, and an minus, means odd and even you are separating. And now when you are writing, with this combination, you are writing B1, B2, B3 and C1, C2, C3, where B1 is an minus 1 into an minus 2 minus an minus 3 divided by this number. So this gives you the coefficient of B1. Same way B2 is an minus 1 into an minus 4 minus an into an minus 5 divided by again the an minus 1. Same way C1 is B1 into an minus 3 minus an minus 1 into B2 divided by the this B1 coefficient, and C2 is an minus 5 into this B1 minus an minus 1 into B3 divided by this V1. So like this, we are going on and calculating the other variables. So this means if you have the third order, so your numbers are A3 and A1, and the other one says A2 and A0. So S3 is corresponding to this, S2 is this. Now S1 we have to find out. S1 is B1, and because B2 is not there, and which we have to calculate here, and S0 is only C1 is there. So what is B1? B1 is A2 into A1 minus A0 into A3 divided by A2. Same way C1 is A2, means this B1 into A0 divided by B1, which just comes out to be A0, because there is not a fifth order term. Otherwise you have the B2 and C2 also. So the requirement for a stable third order system is that the coefficient should be positive, and A2, because you want this should be positive. This means A2, A1 should be greater than A0, A3. And when these are equal, then it results in a marginally stable case. Now we are coming to the nonlinear system, because most important is here the chaos or the uncertainty. So dictionary meaning of chaos is disordered, formless matters supposed to have existed before the ordered uniform, or we can say the complete disorder or utter confusion, or I can say the randomness. Physically, it is a aperiodic long-term behavior in a deterministic system that exhibit sensitive dependence on the initial condition. And what we mean a periodic long-term behavior, that the trajectories which do not settle down to fixed point periodic orbit or quasi-periodic orbits as time tends to infinity. Means we are taking a small change in the initial condition, but the two trajectory which start together are not settled down to a to the some point or the some trajectory. So basically, deterministic, already we know the system which has not noisy inputs or parameter. And if we have a nonlinearity, then always we have a irregular behavior. Sensitive dependence means the nearby trajectories separate exponentially fast. This means for a small change in initial position, like yesterday we have the that point, r is as you are changing the value of the parameter, you are getting a different type of the trajectory. So if this lambda x naught is the initial position, so x naught plus delta change in that at the time of t, as xt changes to xt plus delta xt in such a way, is this delta x naught plus e of lambda t, means these are exponentially away from each other. So that lambda is known as, if it is greater than 0, this is known as a divergence of orbit, or it is also known as a Lipno characteristic exponent. I will explain that. And if it is positive, then always motion is a chaotic. So if we have to talk about this, what are the sources and tools for the nonlinearity? First is phase plane methods. Yesterday I discussed that, but I will take some slides about that. Then the bifurcation diagram, that also we discussed about the logistic map, Poincare maps, double Poincare maps, reduction to one-dimensional map, Lipno exponent, fractal dimension, that also I explained, and the chaos diagrams that I will try to cover some of that. So identification is if you have any chaotic motion or nonlinear system, so that is possible for the nonlinear system. So if a system has nonlinear elements or properties, it may exhibit chaotic behavior. Linear system may sometimes, when you are doing the superposition and the change in the variable, then they can behave like a nonlinear system, and then they will exhibit the chaotic behavior. But no, general normal system can never exhibit the chaotic behavior. When we have the random inputs, if inputs are random, like yesterday we take the r values, as we are taking the random input, then we may get a non-periodic or chaotic response in a deterministic system. Time history also, yesterday I showed that how with the change in the amplitude variation with time, so non-periodicity may lead to the chaos. And phase space, when we are talking this also, yesterday we discussed, if you have a set of points x and x dot, we are saying the momentum, which is the xp. So when the motion is periodic, then phase plane traces out of a closed curve, and chaotic motion have orbits which do not close, and fractals have the self-similarity in the figures, which yesterday we discussed in detail. Limit cycle, yesterday I showed you the example of the pendulum, where you have a limit cycle 1, 2, 5 and other ones. So an isolated periodic orbit is a limit cycle. If you have a 3 limit cycle, it will lead towards the chaotic motion. Fourier spectrum, already we studied the Fourier series and the spectrum. Whenever there is the appearance of the broad spectrum of the frequencies, then we get the chaotic motion. Poincare map, basically it is a set of points xtn versus tn. It is called the Poincare map. If tn is 1 period, then always orbit consists of 1 point. If it is 2 period, it consists of 2 points. But if it is 3 period, then always chaotic motion occurs. So in case of chaos occurring, the Poincare map will consist of neither finite set of points nor a closed orbit. Same way, when we are getting the self-similarity, yesterday we discussed about the self-similarity, and we see that how we are getting a different versions of the fractals. Now, what are the roots of chaos and fractal? Variation of parameters. When the controlling parameter are varied, So then you have the different type of the periodic terms which leads to the chaos. Yesterday we take the example of the logistic map, and there how the changing the value of r, you are getting a different type of the behavior. Firstly it is going to be the extinct and then leading towards the period doubling or the bifurcation. Next is the period doubling phenomena, where this is changing the values from 1 to 2 and like this thing. But this has one number, I will show that, which is known as a Feigenbaum number. So if you have a period doubling or bifurcation, then it is the twice of the original motion, as we see in the case of the cell growth also. One cell is divided into two, 2 to 4. So the critical value of this parameter, which is known as a Feigenbaum number, it is called that if you are getting the Feigenbaum constant as 4.669, then it is becomes the chaotic motion. Quasi-periodics, in general, it is the state attaining the dynamic instability after changing some parameters becomes a limit cycle. Such three simultaneous coupled limit cycle finally produce a chaotic motion. Yesterday we showed you the example of the pendulum where I showed the three limit cycle leads toward the chaotic motion. So if we have a, in simple way, if we have to understand, when the frequency omega 1 and omega 2 of such simultaneous oscillation are not commensurate, the motion is not periodic. It is said to be quasi-periodic. And if the ratio is irrational, it is means if it is not periodic, then it is and if it is irrational, then it is said to be a quasi-periodic. Fixed point already a detector we discussed a lot yesterday. Now there is the double resonance. Basically, if you have the frequencies and if you have the linear combination of that system, for all ai is not equal to 0, then resonance has occurred. And if you have a double resonance, then it leads toward the chaotic situation. Basically, this is the main important theorem. Actually, what is that? If you have a like a perturbed pendulum system, and if you are finding their surfaces, and if these surfaces are non-integrable, then as the perturbation grows, these resonance zones grow and destroy the Km surface around them. And when all Km surfaces is destroyed, then the chaotic motion starts. Now I'm taking, this is an example of Lorentz detector. Here you see that you are not able to predict the motion, that from where this trajectory start and where it is going to be. And if you see that this is the one, but here it starts, and then you are not able to trace which trajectory is going on that. So this means all the surfaces are dissolved, and that's why it is a chaotic motion, or the Lorentz detector is the best example of the chaotic detector. Basically, Lorentz in 1963 is studying about some weather parameters, and he gave a computer some conditions and the three equations, and he left for that. And when he saw, he find out this beautiful picture, and he stuck out with the system that what is that. And someone is saying it as a owl eyes, someone is saying it as a butterfly effect, but this is a basically giving you that when the parameter change is there, then weather becomes the perturbed, and that is become a chaotic situation. Now we are coming to the classical phase system. This is the basically in all our physics and kinematics we are studying. Suppose q1, q2, qn be the generalized coordinate of a system with I degree of freedom, and corresponding p1, p2, pn or their conjugate moment. This means basically if we talk about the, these are the xi's, which is the position component. These are the xi dot, which is the velocity component. So then we have a curve which is a combination of qi, pi, is known as a phase space. So yesterday also Lakveer asked me in this question about that how to plot the phase space. I tried, that's why I took that. When you have a plot between xi and xi dot, then you have a phase space systems. So in two-dimensional space constructed from these two S variables, we got the phase space, and each point in the phase space is corresponding to the microscopic state. And this is the Hamiltonian system. If we are talking about, then we generally denote as H of QP, where Q is the generalized point and P is the generalized momenta. And the motion of phase point along a phase orbit, and it be determined by the canonical equation of motion. And we all know that pi dot is nothing but minus del h by del qi, and qi dot equal to del h of del pi. And that we are studying in kinematics of the study classical dynamics, statics, and this is the Hamiltonian. And with this, we solved many examples of the stability using this. And in the fluid dynamics, we are frequently using this type of the equations. And also in the celestial mechanics, this is the base for the finding the energy system of the any system. So if you have this is suppose any curve is there, this is the phase orbit, and this is the point. So this is the energy surface which we obtained using the Hamiltonian function. And the Hamiltonian shows that the energy remains to be the constant. So your Hamiltonian function means HQP is always remains to be the E. Therefore, the phase orbit must lie on a surface of constant energy, which is also known as a ergodic surfaces. Nearest neighborhood, if we have to find out, suppose this is the curve, and we are taking 2 points in the neighborhood of that when you are plotting. So these are the trajectories, and now you see if you are taking the point of that. So these are the changes in the points, like this, like this, like this. And as you are moving away, this is growing. So this means your direction of the flow is showing that as you are moving away from the initial condition, then these trajectories are moving or exponentially moving away from each other. So if you have to find out the nearest disturbance or neighborhood, what is the distance? It is the distance between the 2 points. So we are taking the norm of xi minus xj, where reference point is xj and the nearest neighborhood point is the xj dash. Initial value means the at the point 0 is the minimum of these values, and same way 1 2 we are getting on the changing of the parameters. So xj plus 1 minus xj plus 1, and the norm, this means the difference in j minus j dash is always greater than the mean period. Now we are coming to the Lipno characteristic exponent, and that is the most important section of the nonlinear dynamics, because it is the basic tool which gives you that whether the motion is the chaotic or a regular motion. So it was named after the Russian engineer Alexander M. Lipnov. A system can have as many as Lipnov exponent as there are the dimension in its phase space. Lipnov exponents are less than 0. Means if it is negative and less than 0, then signify nearby initial condition all converge on one another, and initial small error decreases with time. So as this grows, means if it is positive, this means they are diverging each other. However, if any of the Lipnov exponent is positive, then infinitesimally nearby initial condition diverge from one another exponentially fast. That is, the error in the initial condition will grow with time, and this condition is also known as sensitive dependence on initial condition, which is coined as chaos. So if you have a positive Lipno characteristic exponent, then that is the guarantee of the chaos in the system. But it is not means that is the it is not a stable system, since the eigenvalue of a limit cycle characterize the rate at which nearby trajectories converge or diverge from the cycle. So Lipnov exponents are considered to be generalization of the eigenvalues of steady state and limit cycle solution to the differential equation. And yesterday we calculate all types of the eigenvalues and eigenvectors, and different type of the functions I explained in detail. So Lipnov exponent, if we have considered a system with its orbit xt about a fixed point x star t with a perturbation of u2, et, then the Patab system can be explained as xt equal to x bar t, because this is a fixed point, plus this is the perturbation, so plus ut, where this ut is the perturbation, which is basically implies the average deviation from the unperturbed trajectory at time t. So this is the fixed point, and from this fixed point, how much is the perturbation in the system or deviation, so that we have calculated, and that is giving you the complete orbit system as xt. In a chaotic region, the Lipnov characteristic exponent, which is normally denoted as sigma or lambda, is independent of initial value. It is given by this theorem, Osladek theorem, which states that for an n-dimensional map, the Lipnov characteristic exponent are given by, means your sigma I or lambda I is nothing but limit n tends to infinity log of lambda I of n for I equal to 1 to n, where lambda is the Lipnov characteristic number. Yesterday also we used, when we are calculating the fractal dimension, we use this formula, limit of that log of the numbers divided by log of the magnified numbers. So mathematically implies that it is a dynamical system, is a quantity that characterizes the rate of separation of infinitesimally closed trajectories. So basically, if two trajectories in the phase space have initial separation as delta x naught, then delta x naught diverges at a rate which is given as this one, where lambda is known as a Lipnov exponent. And the rate of separation can be different for different orientation of initial separation vector. Thus, there is a spectrum of Lipnov exponent equal to the number of dimensionality of the phase space. It is common to refer to the largest one as the maximum Lipnov exponent, because it determines a notion of the predictability for a dynamical system. So whatever be the maximum Lipnov exponent, if it is negative, we say that a system is predictable or it is stable. If it is positive, then it has a chaotic behavior. So positive MLA is usually taken as an indication that the system is chaotic. And if we are taking it, it is normally showing the exponential growth rate, or the effect of the other exponent will be obliterated over time. Properties of this, the Lipnov exponents are independent of both the metric used to determine the distance between perturbation and the choice of variable. This property implies they are dynamically invariants, and thereby provided an objective characterization of the corresponding dynamics. So strictly positive maximum Lipnov exponent is the synonymous of exponential instability. But one should be warned that in some special case, this may not be true, as it is given by the uh, Lenovo in 2016, and which is known as a Perron effect. So because this maximum Lipnov exponent is not giving the instability, then we are going to be the different type of the indicators of the Lipnov, which is the, and based on that, then we are trying to finalize that whether the system is chaotic or not. So strictly positive maximum in exponent is always considered as a deterministic chaos. Typical trajectories are characterized by same Lipnov exponent, but there exists a zero major subset with different stability properties. So the infinitely many periodic orbits embedded in a chaotic character are the example of different type of the trajectories. This is the characteristic or one-dimensional map. If we are taking xn plus 1 equal to g of xn, then easily we can characterize the Lipnov exponent, which is equal to the average of the rate of change, which is dg by dx log of that. The sum of all Lipnov exponent measure the contraction rate of the volume in the whole phase space. So if it is less than 0, this means these are coming closer. So the trajectory shrink exponentially to 0. In the Hamiltonian system, if it is equal to 0, then we say clearly that volumes are preserved, which is known as a Liverless theorem. And in general, if Lipnov exponent is greater than 0, then the sum of this, then we are saying that it is a chaotic system. So Lipnov exponent come in pairs such that their sum is equal to 0. This means the Lyapunov spectrum is symmetric in a way of emphasizing the invariance of Hamiltonian dynamics under change of the time arrow. And we know that how important is about the time arrow, because recently, last year, the Nobel Prize is given on that Chandrasekhar theory for time arrow. So if you are taking about that, it is also proving that how much bifurcation occurs from the some point of the linear stability. Now we are taking this system, how we have to measure the relative stability of the dynamical system. Now what we are taking, suppose these are the two trajectories. This is the point x naught and this is x naught plus u naught, where u naught is a very small change. If we start two initial trajectory with the same initial conditions and with the very slight change in these initial condition, suppose this is a 0.001 and this is 0.0001, so both the trajectory are nearby, very close. But in the long run, if you see that this is the change in the trajectory from x naught to this fx naught, and this is the change. So if you see that whatever be the this distance, this is giving you the rate of the convergence, or of the that how much rate is changing from this point to this point. So generalization of the eigenvalue of steady state and limit cycle solution of differential equation. The most direct indicator and quantifiers of deterministic chaos. The number of Lipnov exponent depends on the dimension of the phase space of the system. So basically what you are taking, at each set of vectors, you are finding the change. So initially this is the delta R naught, means the initial value. Then after the first step, you got the delta R1, then delta R2, delta R3, and like this thing. If they are coming closer, then you say it is a stable system. But if it is moving apart, then it is a showing a instability in the system. So Lipnov exponent, these are the two conditions, and denote is the initial condition or initial change in the two trajectories. But dt is giving you the final change in the nearby trajectories. So it is usually defined as lambda equal to, which is the component, equal to limit this t tends to infinity, means how, what is the behavior in long range, 1 by t log of dt by d naught. Means the, if this ratio remains to be the same, then this is a, basically your trajectories are the closer to each other, and you are saying a system is a stable system, because dt is nothing but it comes to be d naught of exponent of n times of t minus t naught. So if this exponent factor is coming to be the 0, this means the two trajectories are closer to each other. Otherwise, these are moving apart from each other. So lambda equal to n and lambda equal to 0 otherwise. This is the algorithm for calculation of the Lipnov characteristic exponent, and for this I gave the program completely, which is given by the Wolf. Let xn equal to fn of x naught, means xn is the series of the points which is depending on the initial condition x naught, and yn is another series which is dependent on the variable y naught. This gives the nth iteration of orbit of x naught and y naught under the function f, and the condition are such that the initial values are very close, means x naught minus y naught are very close. And same way, if xn minus yn is remains to be close, then we are saying that these are following the condition of the stability. Then we are calculating the nth iteration for one dimensional system, which is given as mod of xn minus 1, which is approximately t equal to 0 to n minus 1 mod of f dash t x naught minus y naught. Basically, as these are depending on the x naught, y naught, so we are getting like yesterday I showed that f is x naught, y naught, f dash is miss, or f1 is the first derivative of that, and like this you are getting the different trajectory, where x and yn are respectively the nth iteration of orbit x n naught and y naught under the function f. Then we are taking the exponential separation rate, which is defined as the log of mod f dash x of two nearby initial condition averaged over the entire trajectory, which is given as lambda x naught equal to limit n tends to infinity 1 by n log product of mod of f dash xt, because x naught minus y naught is giving you that it is very close to 1. So that's why we are leaving that. And where this product is nothing but e of lambda x naught of n, and for n greater than 1. So the defined this lambda x naught is known as a or Lipno characteristic exponent of orbit x naught. So this is the complete algorithm for finding the Lipno characteristic exponent of any given series. And this is the process which we are applying in generally in finding the vectors. So it is the gram skimmed reorthonormalization. Suppose given a set u1, u2 up to un of n linearly independent vectors in the Rn, the Gram-Schmidt procedure generates an orthonormal set v1, v2, vn of vectors which span this complete set which is generated by u1, u2, n. So what you are defining? You are defining the vectors w as w1 is the u1 itself, v1 is norm of w1, means v1 is the orthonormal vector which is w1 divided by the norm of w2. So w1. w2 is nothing but u2 minus, this is a Poincare bracket of u2 v1 into v1, and v2 is defined as w2 divided by norm of w2. Same way we are defining the vector wp, which is nothing but up minus product of inner product of up, means sum of ups with vi and vi, and vp is nothing but wp over norm of vp, and where this is nothing but the scalar product of the vectors. If Lipnov exponent are less than 0, it means nearby initial condition all converge on one another, and initial small error decrease with time. And if it is positive, then of course it is a chaotic motion. And this yesterday also discussed the behavior of the attractors as per eigenvalue. If all eigenvalues are less than 0, you are getting an equilibrium state. If one is 0, but all other are negative, then you are getting a one period limit cycle. If k values are 0, but all are negative, then you are getting k periodic cycle. But if one value is positive, but the sum is negative, then you are getting a strange chaotic. If any one value of this Lipnov is positive, then always you have a chaotic system. And if two are positive and this sum is negative, you are getting a hyperchaotic system. And you see this is the simple curve is given. Suppose it is the feedback strength, and these are the Lipnov exponent. Here you see the different value. Up to here, as you have the lambda as a negative value, so you have a steady state. You see that up to 0, you have a steady state. This one. In this period, you are at a 0. So you have a periodic cycle. This is the example here. But in this, you have the positive one. So see that this is a chaotic one. So this is the complete picture where you have the all three type of the signal strength in the case of the composition of the feedback strength. This is the k periodic state. You have the different states, like these are the, here this is 0, this is 0, but the sum is if you are taking sum, or the values are positive, but the still you are getting its value is here. So you are getting this type of the structure. Miss, two are the main values which you have here. Now we are coming to the numerical calculation. So it is, I am giving you, this is the algorithm, or that start with any initial condition in the basin of attraction. Then we are finding the orbit and the attractor. Select the nearby points. Advance both orbit, as we have discussed about the using the Gram orthonormalization. This is giving you the complete one. And this is the paper, and it is published in Physica in the year 1985. Wolf gave basically the first idea about determining of Lipnov exponent from a time series. So this is the algorithm and the program which is given by Wolf, and this is the algorithm employed as and this is giving the complete Lipnov exponent. And this I have applied, means this is the program for the Lorentz, which is used by the Lorentz. So what they have, this is the basically the function. They are calculating the Jacobian of that system. Then they are finding the variational equation, which is used as this Jacobian into the y vector, which is the square matrix with the same dimension. And correspondingly, they are finding the values as, means these are going constant sigma value they are giving as a 10. R is this value which they are given as 28. This is beta value which they have given as a 8 by 3. And now the vector are x as x1, y as x2, and z as x3. So your vectors are x1, x2, x3. So they generate because three vectors are given, they are generating a square matrix, which is a vectors x4, x5, x6, x7, x8, x9, x10, x11, x12. And then they are finding here they are writing the function. You see that f1 is sigma, means this sigma into y minus x. f2 is rx minus xz plus rx minus y, because they have used a capital R, that's why they changed it here r. And this is third one is x bar y, xy minus, because they have used beta, so beta of z. So Jacobian is nothing, but this is the Jacobian. They are writing minus sigma, sigma 0, r minus z, minus 1 minus x, y x minus b, beta. And f4 to L, they have calculated, means from 4 to 12, they have calculated using this one. So that is basically a Lipnov exponent. And then they do the T res, which is using this Lipnov exponent function. And then they are calculating the different type of the functions. So this is the complete program. Now, because in 2006, in some example, it is showing that it is not showing clearly the chaotic chaos. Then they discussed about the Lipnov indicators. There are the different type of the indicator. First is the DLI, which is known as a dynamic Lipnov indicator. It is defined by the pattern found by the largest eigenvalue. So algorithm is JB the Jacobian matrix. At every time, we calculate the eigenvalue of the matrix, and then we plot the largest eigenvalue. So eigenvalue of the Jacobian matrix is calculated using this formula. If these eigenvalue form a definite pattern, then the motion is regular. Otherwise, it is showing a chaotic behavior. So what you have at each point, you are calculating the eigenvalues at each point, and then you are trying to plot that curves. Another one indicator is the fast Lipnov indicator. It is basically given the largest eigenvalue. Dynamic Lipnov indicator is giving the largest eigenvalue, and fast Lipnov indicator is giving the largest eigenvector. A same iteration process we are using. You are finding a p-dimensional basis embedded with n-dimensional space. Then we are finding the supremum of these vectors, and which is the eigenvector. And then we try to find out, and if regular orbit, this has a relatively small values. If it is increasing exponentially, then we have a chaotic behavior. And as t tends to 0, if you're not able to compute the limit value, then it has registered that it is showing a chaotic system. Now here at each iteration, you are finding the eigenvectors, and then you are finding the distance as this ratio, which is giving you the value of the eigenvector. Next is the SALI, which is known as a small aligned index. and it is nothing but it is giving the and this is the most important tool to distinguish between order and chaotic motion at each time evolution. What we are doing in this case, we are taking n-dimensional phase space. Consider the orbit in the space. We are calculating its derivation vector, means how much deviated it is, and then we are calculating the value at each steps. So it is Sally is nothing but minimum of the deviation, means the orthonormal vector of the deviation, sum of all those things. So sigma 1 by t, norm of that, this is plus sigma 2, and the difference of this means whatever be the deviation, you are taking the maximum and minimum of that, means by summing the two deviation and differencing the two deviation and then taking the minimum of that. So this property of time evolution of cell clearly distinguish between order and chaotic motion. So for chaotic orbits, Sally value tends to 0. And if you are getting a non-zero value for the, then it has fluctuates. And in case of 2D map, Sally tends to 0, both for ordered and chaotic orbit, and completely different time rates. I will show you the case. Here at each point means basically what you are doing, you are finding the eigenvalue as well as eigenvectors at each step, and then you are taking the difference of the deviation from the mean value, the sum, and then finding the minimum value. Now I'm coming to the, yesterday we did this formula, recursive formula, where we have used x equal to x square plus 1 as an example. And as we are changing the value x, then you are getting the different value. Suppose right side is x is 1, so left hand side is the 2. If you have a 2, then it is a 5. If you have a 5, then it is a 26. If you have a 26, then it is 677. And if 677, you are getting the 4,58,330. Mandelbrot, basically, as yesterday also I said that he is known as a father of the fractal. He used the IBM computer and graphed this equation. He plotted this equation, x equal to x square plus c. See the beauty of this equation. He graphed the equation x equal to x square plus c, and he got this curve. And the beauty of this curve, it is not closed anywhere. Means as you are moving inside, you are getting the open ends. And see this. This is the simple equation. Xt plus 1 equal to xt square plus c, where c is the different values as you are plotting it. So you are getting this curve. And see the beauty of this. It is not a closed one. Yesterday we discussed if C is the 0, you get a convergence because all are converging. If you have the C as 1, then it is converging, means it is a 1, 2, 5, 26. So it is a divergent. If you have a -1, then it is oscillating, like different points you are calculating. And this is the known as a Mandelbrot set on his name. And now you see the beauty. If you zoom in any part of that, this is a small part. If you zoom in this part, see the beauty of this equation. You got this structure. Now you take any small part and zoom in. You got this structure. Again, inside of that, you are getting similar structure again. If again you are zooming in, you are getting this structure. So this means this is the beauty, that it is not a closed curve. That's why you are having the self-repeated structure. In our life also, like in nature also, if any hazardous occurred like tsunami and other things, then again you have an order within that disaster, and that's why life continues. And even during this pandemic, you see that there is the order within the disorder. So as we discussed about this thing, I think this is repeated. Now we are discussing the stability of the nonlinear system. So if we have to discuss about the nonlinear systems, then first Lipno method, which is based on the linearization. To examine the stability of nonlinear system, we have to use more complicated tools than the linear ones. So what we are doing, any nonlinear system, in the first step, we transform it to the linearization. by using the method of linearization, which is sometimes also called the first Lipno method. Principle is expanding of the right-hand side function of the equation of motion around the fixed point into the Taylor series with respect to neglecting the higher order members. Suppose any function is given, we are expanding that using the Taylor series and around this point. This is your fixed point or equilibrium point. So it is nothing f of x bar plus del f by del x with x minus x bar and like this thing. Now what we are doing? We are neglecting the higher term series. So we are taking only this function. So this is we are doing as a linearization of the given system. Then we are finding by putting fx bar equal to 0 as the point of the equilibrium. So dx by dt equal to fx. So since this is 0, so you are getting simply this function del f by del x of x minus x bar. Now since this is 0, this means dx minus dx bar by this, which is dx by dt. So simply you are getting this equation. And now if you are finding this is your original system. And linearized system of this one is del f1 by del x1 at this point plus all these del fn, like this one. Now you are creating the Jacobian of this. If you are creating the Jacobian, so this is del f1 by del x1, del f1 by del x2, and del f1 by del xn. Yesterday we discussed this Jacobian, which is giving you the value of the nonlinear system as a df and dfx bar. Now we are calculating at that point, and which is this one. So this system at that equilibrium point, you are calculating the value. So suppose I am taking a simple example, y minus 1 and y plus 1. So of course your 2 points are y equal to 1 and minus 1. So this is a minus 1 and this is the 1. Now we know that this is a stable fixed point because the trajectory are coming closer here, and this is a unstable fixed point. So that it is showing y dot equal to fy because the trajectories are moving apart from this point. Now I am taking a simple pendulum case. Yesterday we discussed about that. It is a simple pendulum equation. Phi double dot plus omega naught square sine phi equal to 0, where omega naught square is nothing but g by L, or this is known as a constant of gyration. So if we are transforming it into the two equation, phi dot equal to omega, another one is omega dot equal to minus of omega naught square sine phi. And when you are equating it to 0, then phi dot equal to omega, and then omega naught equal to, you are taking omega, means this value omega naught square as minus 0.26. Now see that these are the different basin of attractions you are getting. This is the separatrix. These are the different basin of attractions. At the different points, you are getting a different behavior. It is a limit cycles. Here, these are exponentially diverging from each other. So these are the different types of the structures which you are getting for this type of the pendulum equation. Now, as we are changing the different initial condition, suppose phi naught equal to 0, you are getting a fixed point. If phi naught is 45, you are getting a limit cycle. You see the one limit cycle. If phi naught equal to 90, then again you are getting a limit cycle, but that speed grows. If phi naught equal to 135, again you are getting a limit cycle, but the spectrum or the basin is larger. If phi naught is 170, then you are getting a tractor as of this one, but dimension changes. You see, earlier it is moving from here to there. Here it is moving from upward to downward direction. If phi naught equal to 190, now see the changes in the basin. Here you have the closed trajectory. Here it comes to be the sine curves. Directly it is changing the value. But if you have phi naught equal to 220, again it is the same spectrum, but changing the dimension. But if you have phi naught equal to 180, then you have an unstable fixed point. So at 0, you have a stable fixed point. At 180, you have an unstable fixed point. Now, I'm taking a very simple example to show that how we have to make the linearization of the system. Suppose we take x1 dot equal to x1 square plus x2 square minus 1 divided by x2 dot equal to x1 minus x2. Now we are making the linearization of system. Firstly, we are finding the equilibrium point. So f1x is this one, f2x is this one. When you are equating 0, so from this equation you are getting x1 equal to x2. When you are substituting x1 equal to x2, from here you got 2x1 square equal to 1. This means x1 is plus minus 1 by root 2. So your points are 1 by root 2, 1 by root 2, and minus 1 by root 2, minus 1 by root 2. So you got these two fixed points. One is roughly 0.7 and minus 0.7. Now we are calculating the Jacobian matrix based on that. What is the first value? 2x1, then 2x2. It is 1 and minus 1. So this is your DF, which is 2x1, 2x2, 1 and minus 1. Now we have to calculate at the equilibrium points. So at the point 1 by root 2, 1 by root 2, it comes to be this value. And when you are solving it, your eigenvalues are approximately 1.9016 and minus 1.84. So this means it is a opposite signs. One is a positive and one negative value. And since you have a positive eigenvalue, that's why system is unstable here. Now for the second point, it is minus 1 by root 2, minus 1 by root 2. You got this matrix. And when you are solving, you are getting plus this is this and plus minus of this iota. So you are getting a complex root because it is a complex eigenvalue with negative real part. So the system is stable. Because if you have a positive real part, then it is an unstable system. Now, if you are coming to the damped harmonic oscillator, that is easier for the earlier system. So then this linearization failed here. So we are going to the another method. Suppose we have a system x dot equal to v dot equal to minus x minus mu v cube. Now as we are putting it 0, so your system is xv. And when you are taking f of xv, it is v and minus x minus mu v cube. And when you are putting it 0, v is 0. And when v is 0, x is 0. So you are getting a simple one fixed point, which is 0, 0. Now if we are using this point and then we try to find out the stability or instability of the system. If you are finding the Jacobian, so it is 0 and 1. It is minus 1 and minus 3 mu v square. So point r at the point 0, 0, it is 0, 1, minus 1. And when you are putting v0, it is 0. So if you are solving it, what is the eigenvalues you are getting? Plus minus iota. So they have 0 real part, and the method of linearization, this means cannot decide about the stability. So we have to move further. So what we are doing, we are changing the value, and this is the trajectory. We have to find out about the 0, 0. You see that this is the origin, and near to that you are getting a limit cycle, but after some time you are getting they are exponentially diverging from each other. So now we have to find out what kind of the behavior it has. As this is not giving you the solution, so we are trying to find out the Lipno function. So we are using the second Lipno method. First one is the linearization method. Second is the energy method, where we are using the potential function. So at this point, we are trying to find out the energy function. So what is the second Lipno method? Is to find out this Vx, which is known as a potential function that represent energy or generalized energy, which satisfy the following conditions. First is that it should be continuously differentiable about the fixed point. Second, it should be positive definite for all values of that, and the value at the fixed point should be 0. Third condition is if it is means the rate of change should be the negative definite for all states of this eigenvector, and at that point it should be 0. So if you are taking at any state x is not equal to x bar, where if you have dv by dt equal to 0, then the third condition is considered satisfied if the system immediately moves to a dv by dt less than state 0. So And then we say that it is known as a stable condition. Now we are taking a energy of this harmonic oscillator. So it comes to be the kinetic energy plus potential energy. So you know that kinetic energy of the system is half kx square and potential energy is half mv square. So if we simplify, hello, 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 some noise is there. Hello, someone has opened the mic or some noise is there.
சார் ஒரு போட்டோ எடுத்துக்கிறேன்.
Hello. Dr. Lakveer. Hello.
Hello, Karthik sir. Please turn off your.
Yeah, some disturbance is there.
Yeah, ma'am. He is turn off the mic.
Yeah. So if you are taking this system, it is simply if you are taking m and k as 1. So your system is simply half of x square plus v square, which is the energy system. Now we are taking this function, and we know that at the 0, 0, it is continuously differentiable around the point 0 and positive for all states except for the fixed point. So this means the first and second condition are satisfied. So we have to use the Lyapunov function. Now dE by dt, if you are taking, what is the derivative? Del E by del x into dx by dt plus del E by del v into dv by dt. So now you calculate this. What is the del E by del x? It is x. Del E by del v is also v. So you are getting, and dx by dt is your v, because earlier we have equation, and dv by dt is this one. So now we are putting this equation and finding the dE by dt. So dE by dt comes to be del E by del x is x, dx by dt is v. So it is xv plus like this function. This cancel out, you directly have only minus mu of v4 function. So dE by dt is nothing but comes to be this one, which is a negative definite. So we can see that this is always be negative except at v equal to 0, where dE by dt is 0. So this is also satisfying all the three conditions. At the fixed point, you have the uniformity, means continuity. Then we have the spring is maximally compressed, and at the instant where the spring is maximally extended. So situation 2 and 3 and all these conditions are satisfied. Now we are finding that because you are getting this Lipno exponent function, the second function v, so this satisfied that 0, 0 is coming to be the stable function. So see that same example, even the point is 0, 0, but we require so many conditions to check its stability. Now, how do we estimate this function? As we told about this is the function Vx bar, which is suppose the potential function, as it is the sum of kinetic energy and potential energy. So it is nothing but the sum of the vectors. So if we are taking, we are finding the origin. So we are taking about that perturbed point, we are expanding that function. And this is the general form of the this exponential functions. So our function is because we are using the quadratic forms also. So these are the different type of the functions you can have. This is for 0, this is about some general point, this is the general function, and this is the different form when you are using. So of course easier is the first one, then the second, and as you are growing, then the complexity grows for finding these solutions. Now this is the damped pendulum. Earlier we have discussed only up to this and this function. Now this is the part which is giving the dampness. So if you are having Then again, you have these type 2 of the systems. These as values are changing. And again, you are solving it using those method. Only I am showing that how your original and these are different. So here, see, there you are getting a limit cycle. Here you are getting a functions which are moving away from that. Now we are coming to bifurcation. Yesterday, I only gave you the glimpses that what is the bifurcation. Today, I am going to discuss about that, how you are finding the different values of the bifurcation system. Yesterday, I took this example that here you have a value. So it is up to 1 point something. Its value is tending towards the 0. That's why it is a catastrophe, extinct state. From this to this, it is no catastrophe or only oscillations. After that, it is a period doubling phenomena where your curve is dividing into 2 and 3.2, then 3.5, then 3.55, like this thing, you are getting this one. So this is the where you are getting an extinct position, because this is tending towards 0. Here it is oscillating. And after that, you have a non-periodic forms. Now, what are the different type of the bifurcation? There are the 2 different type of the bifurcation mainly, which is a global bifurcation, and another one is a local bifurcation. Yesterday, I talked about that. Now I am coming to be this example already I have taken, logistic equation. And then we find out the formula of this one and try to find out the bifurcation of this, which shows this one. Yesterday, I gave in detail about how different point you got the different values. So you see that up to r less than 1, you are getting extinct value. 1 to 3, you are getting a fixed point area. From 3 to 3.57, you get the different type of oscillation, means here 2 to 4, 4 to 8, like this thing. And when you have 3.57 to 4, you're getting a chaotic zone. And again, for higher values, you are getting the becomes. So up to that, again, you are getting the similar way. So after that, if you are going, you are not able to find out any trajectories. Now I'm coming to the different type of bifurcation. These are the mainly which we have discussed, which are normally discussed in the nonlinear system. First is known as a saddle node or fold bifurcation. Another one is a period doubling of lip bifurcation. Third one is the pitchfork bifurcation. Next one is the transcritical bifurcation, and the last one is the Hopf bifurcation. One by one, I am taking the same example as I have took yesterday and trying to explain these things. Now, first is the fold bifurcation. And in this bifurcation, you have 2 fixed points which collide and annihilate each other. Suppose you have a differential equation, dx by dt equal to r plus x square. Now, if you are solving it, what you are getting? If you have r is less than 0, so x is plus minus r, root r. So this is you are getting x equal to minus of under root of minus r and plus of under root of minus r. So this means you are having stability at this point and unstable at this point. See that since r is negative, okay, and the points are minus of this negative means this is a positive root of negative. So if you have negative root, here you have a stable form up to here. But if you have a positive one, you are having a unstable point. But if you have r greater than 0, so there are no fixed point. That's why you are not getting any point here. So here you have a fold bifurcation around the origin. If you are able to fold this one. So this is a fold bifurcation example. Directly you see that. Now suppose you have a differential equation dx1 by dt equal to minus x1 and dx2 by dt equal to minus 2 plus x2 square. As this is the example of this. So if you are solving, putting the point, so x1 is 0 and x2 is under root of plus minus root 2. So you are getting these two as a fixed point. This is your Jacobian matrix. At this point, you are getting this structure. So your eigenvalues are minus 1 and 2 root 2. And since you have a positive eigenvalue, that's why you have the unstable structure at this point. So this is a saddle point since there is a real eigenvalue of variable sign. Now if you are using the XP, you have this. So your point are -1 and -2√2. And it is an attracting node because you have the real eigenvalue, but both of a negative sign. So this is a saddle point with a node. So here you are getting the example as a saddle node bifurcation for this function is this one. So here you have a positive one and this is the negative one, and this is again a saddle node bifurcation. Now, if you have a period doubling, yesterday we discussed a lot about this thing, which is r xn into 1 minus xn. So you have a period doubling phenomena here. Now, suppose you have an equation of the form rx minus xq. In this bifurcation, one fixed point is split into three various ones. So like here, if you have one point is x is 0, another is r minus x square. So if r is negative, there is just one stable fixed point, which is x equal to 0. But if r is positive, then again you have a one is at x equal to 0 and two other stable points are plus minus under root of r. So one is x equal to 0, then both are this one. So this is type of the Pitchcoff. I think in the physics practicals, everyone we have used this Pitchcoff. So this is a Pitchcoff bifurcation. Another one is the case of the same one, but here you have Rx plus Xq. So again, you have for R positive, there is only one, which is X equal to 0. So this is, and this for R less than 0, these are also unstable point. That's why you have this one. And this is basically a folded type of the case. But normally we are using the first one, not this one, but this is also showing a bifurcation. Because you have a curve around this point. Next one is the transcriptical bifurcation. In this bifurcation, there is a one stable and one unstable fixed point. And when they collide, they change their stability. So what is the equation? dx by dt equal to rx minus x square. So one point is x equal to 0. And another one is if r is less than 0. So you get x equal to r as an unstable point. So x equal to 0 is there. But if r is positive, then you have x equal to 0 and x equal to r. So which is this one. So x equal to 0 as an unstable point for this one, but x equal to r is the stable point. So one is a 0 and this one, another is this one and this one. So here this is stable and this is unstable. But after colliding at this point, it is stable and this is unstable. This is very important because most of the cases are governed by this equation. So it is a two-dimensional one. And in this case, a single fixed point changes it to a limit cycle or vice versa. Suppose you have this type of the example. And if you have to find out the fixed point, so you're getting origin, so 0, 0. Now we have to check its value. So it is r minus 3x1 square minus x2 square. And another one is -1 minus 2x1 x2. Same way here when you are taking 1 minus 2x1 x2. And this one is r minus x1 square minus 3x2 square. So this is the Jacobian matrix. Now at this point, if you are taking, this is 0, this is 0. So it is simple r minus 1, 1 minus r. So you are getting this matrix. Now if you are calculating its eigenvectors, so I think you are getting, this is the value, r plus minus iota. Now if r is positive, then it is unstable. If r is negative, then only you are getting a stable fixed point. So if you are finding this, again to check it's because it is not giving the stability. So for decide about that, r should be 0. So you are getting this as a Lipno function. Finding again the values, you are getting this as a function value. For r equal to 0, dv by dt is outside the fixed point, which is always negative. Hence, we have a Lipno function. So for r equal to 0, you are getting a fixed point, which is Lipno stable. So it is asymptotically stable at r equal to 0, 2. And these are the different phases. If r is minus 0.1, so you are getting a stable phase because this is a stable attractor. For r equal to 0, as you are getting a marginally stable, so asymptotically you are getting, it is a limit cycle, not tending to that, but it is moving around that limit cycles. But if r is plus 0.1, then you are getting a bigger cycles. But r is 0.1, so you are getting a exponentially as a cycles are growing as the value of x naught are changing, means the initial values as you are changing. And this is the 3D interpretation of this Hopf bifurcation around the horizon. You see that how different adjectives we are getting it. So this is the general rule for concerning about the bifurcation. If you have a continuous system, a local bifurcation appears when eigenvalue has 0 real part. If the eigenvalue is 0, then there is a saddle node, Pitchcoff or transcriptical bifurcation. If eigenvalue have 0 real part, but they are complex conjugate, then there is a Hopf bifurcation. So this is the, for continuous system, you have how the different type of the bifurcation, easily you can check or verify that. In case of discrete system, if a local bifurcation appears when the modulus of eigenvalue is equal to 1, if eigenvalue is plus 1, so then you have saddle node, Pitchcoff or transcriptical bifurcation. If eigenvalue is minus 1, then you have a period doubling bifurcation. And if two complex conjugate eigenvalues with modulus equal to 1, then there is a Hopf bifurcation. So this is a simple rule for finding the for continuous system and discrete system. And this is given that how you have for continuous dynamical system, you have a this one, image of this one. Period doubling means this is saddle and node because you have a eigenvalues as 0. Here you have a eigenvalues is 0, but this is a value has a real part, so that's why you have a only imaginary part. That's why you have a period doubling. And since complex conjugate are there, that's why you have a Hopf bifurcation. Same for discrete dynamical system, you have here, and this one is when you have a complex conjugate of each other with a modulus as 1. This is the simple forms of these ones, you can easily verify. This is the function. So if mu is less than 0, you are getting a stable form. These are when you have a different form, so stable, unstable. This is when this type of the example, so you have a Pitchcoff bifurcation. So you have this stable and these two stables. If you have a plus sign of that, so you have only this stable and these are unstable forms. Now I'm coming to be this example of the logistic map. And we try to find out the different type of the functions based on that. This is your nonlinear map and it is mu x into 1 minus x. Normally x lies between 0 to 1 because otherwise it is not defined, and the mu value is 0 to 4. So this is the logistic map where you are taking these functions. And when we are finding this one, because it is a common equation which is used in the population dynamics, if you have a different parameters B and C, B is the birth rate and C is considered to be the death rate. And normally in any kind of, I'm not saying only epidemiological modeling, but ecological modeling, normally we are taking the growth rate. Here we have taken both the rate are same, is the population growth and decay. But in this case, it is changing. Then if you have to find out, then how you have to explore the logistic maps. So these are the different example. If you are taking initial conditions, mu equal to 0.8 and x naught as 0.17, so you see that it proceed vertically. And how you have to find out? a simple, this is 0.7. See this one, and this is very important. You take this when it is meeting the curve, this one. Again, from that you draw a vertical line where it will meet. So proceed vertical until you hit fx, then proceed horizontally when you hit y equal to x. So y equal to x is this line. If you are meeting that here, then again you repeat this process. I will show that how you are getting a different type of the curve. See that here you are meeting this one, then you are coming this one, then again and again, again and again and again. So you are coming to this 0 point. So it is a fixed point. Here in this case, you are meeting this curve, then on this line, then curve, then on this line like this. So you are converging to this point. So this is a fixed point. Here you are meeting this one, then here, then here, then here, then here, then here, then here. So you are getting 2 cycles. So some are here, some are this one. Here, in this case, you are getting a chaotic situation. So this is clearly giving you how you are finding the different points. So of course, again, we have to check the stability. I think now you are able to do the stability of these points by using the same method, either the linearization or the using the second method, energy method. This is giving you the complete one. Here it is showing how the period doubling is here. Here it is going on a stable one. Here only 2 points are always there. This is a bifurcation also, you are getting it. And this is the complete picture of a bifurcation diagram. Here is stable point. Then you have this as a bifurcation to the 2 points. Here you have a 2 points. Here you have so many points. So different type of the structures, you are getting different type of the behavior. Now, basically, as I told you, the chaos is a periodic long-term behavior. And simple, I am giving you a simple, very simple example. Suppose you have any straight line or I say a paper from 0 to 1. You fold it in between. So 0 to half. So it is 0 to half. You have another one. Now again fold it. So you have this one like this. So again and again you are doing the same process of the repetition of the folding of that. And if you someone asked which is which fold, then you are not able to tell that. So it is a simple condition of the chaotic one. And like in the bakeries, when we are making the pastries or patties, then they are using this method of rolling and stretching and again the same process. So this is a one-dimensional map. Again, we discussed a lot about that. Now I'm coming to Covab diagram. Already I explained that. What do you have to do? You have to start with some point. Take the point where it meets to the trajectory. Then take the horizontal line where it meets to the line y equal to x. Then again, then this, then this, then this, then this, like this. So if it is converging towards the point, that is considered to be a fixed point. And if it is converging to more than 1 point, so this is a fixed orbit. If it is converging to more than 1 point, then whatever be the point, accordingly you are getting the different type of the cycles. So these are the examples. This is the example. This is the example. This is the example. See that I'm giving you all these ones. So there are the 16 various cycling values. And in this case, you are not able to calculate all the values. So it is a, here you have 2 cycles, here you have the 4 cycles. Already I gave the example yesterday. Here you are getting the 16 cycle, and this is the chaotic situation at 3.97. You are not able to calculate that. And this is the where you are getting the period doubling phenomena. Repetition of this, that is calculated using the Feigenbaum constant, and which is equal to limit of an over an plus 1 as n tends to infinity, and this value is called as a 2.50, and this value is known as a Feigenbaum constant. And as this value moves towards the 4.669, then the chaos starts. This is Lorentz detector, already I explained. This is the periods of limit cycles. Different of this. This is the Lorentz impact on the 3-dimension, and it is known as a Oxide. These are the bifurcation for Lorentz dimension, Lorentz curve, and this is how we have to check the stability of these points. This is the curve. You are putting equal to 0, you are getting these. Then you are using the linearization of these ones. And for different values, we are getting different points. Now we are coming about the manifolds. I am not going in much detail about the manifolds. It is simply a topological space that locally resembles Euclidean space near each point. More precisely, each point of n-dimensional manifold has a neighborhood that is homeomorphic to the Euclidean space of dimension n. In this more precise terminology, manifold is referred as a n-manifold. So if you are taking a one-dimensional manifold, it is having a crossing point, which are locally homomorphic to the Euclidean one space. I am showing only that you are able to know about the manifolds. Basically, suppose you have any two-dimensional linear system which is of this form. So this is the matrix of this, and this is the xy. Such a system is linear in the sense if x1, x2 are the solution, then so is any linear combination of that. So solution of x dot equal to ax can be visualized as trajectory moving in the xy plane, which is we know as a phase plane. Suppose we take this example of the pendulum. So mx double dot equal to minus kx. If you are finding this one, and so your equation x dot equal to v and v dot equal to minus kx by m. And when you are finding its solution, means this is the x dot v. So you have to plot v and minus omega square. And this is the plotting. Now you see that on the x-axis when v equal to 0, this is. So you are getting, these are the trajectories. So because you are getting 0, as x gets larger in magnitude, the vector 0 minus omega square gets longer. So you are getting this as a trajectory. So v0, which points to the right when v is greater than 0, and to the left when v is less than 0. So you are getting the different type of the trajectory as you see, and as x is varying, you are getting a larger and larger of the trajectories. To find the trajectories means this is the way you see that. So this is a fixed point. These are the closed orbits we are getting. Same way, if you are taking at a point 0, 0 and using the energy conservation formula, then you are getting these ones. This is for this position. This is for this position. This is for this position, means this is at the pi value. This is at the, you can say 0 or pi by 2, like this. If you are taking this is pi, and this is as a 3 pi by 2. Same way you have this graph where this a varies from minus infinity to infinity. So as this value varies, you are getting the different type of the systems. And I think I tried to show there. If a is less than -1, you are getting a system which is moving towards this. All the trajectory are moving towards this point. So it is a stable node. If you have a equal to -1, so you have this, but it is a stable node or a star, you can say. If a is between -1 to 0, again it is a stable because all are moving towards that. But in this case, you are showing that it is a node, but decay after some time. These all are moving towards this point. But if a equal to 0, so you are getting this point, and so these are all only about the vertical lines only. So again, it is a fixed point. But if it is a is greater than 0, so see that all the trajectories are moving away from it. So it is a unstable point. So this is a saddle point. Some are moving, means these are moving, these are moving away from it. So this is the simply you yesterday also I discussed a lot about that. So these are stable or unstable manifolds you can discuss. I'm only showing you, not going in much detail. Basically where you have the this one, human faces, speech waveforms, global climate pattern, gene distributions, and now in the pattern analysis also we are using manifold study. And this is the basically here we are using either the cluster techniques, which is principal component analysis and density estimation. And if you have a low dimensional manifold, we are using linear and nonlinear curves. So it is a topological space which is locally Euclidean. This is a Euclidean space or concept of submanifolds are there. This is a principal component analysis or eigenvector decomposition we are using. So it is used in the graph theories, and now in all our Google search, or you can say in a social media, you are using the PCA, principal component analysis. And this is the how to find out the optimization of the distance between the two. Means suppose a person has to move to the different cities, then how they have to use the minimum distance criteria. So this is the Dijkstra rule which we are using, and in computer we are using the depth first search, DFS or BFS, either depth search or the breadth search, using these formulas. This is to how to preserve the structure, which is like one distance is this and one distance is this. So how you are measuring this distance, because these are not in the same space. So these are the different type of the embeddings which we are using in the manifolds, but I'm not going, because if I have to touch that point, it will not be covered completely. So I'm not going in much of that. Only I'm giving you the glimpses like how we have to find out the distance of these points. If it is in a simple plane, you are easily able to calculate. But if it is in a space, then you have to calculate the distance in this manner. So see that if it is in a space, you have to calculate this thing. But if it is in a plane, you are getting this thing. So simply manifold is a topological space which is locally Euclidean. So always fit locally, think globally, which is normally a pattern also. These are also the distance rules. All these are the distance rule, how to find out the different type of the structures. And these are the different type of embedding which are formed, isometric or the conformal. So isometric embedding means you have the limit cycles form, but conformal is moving away of that. So these are the different images of this one. And this is showing how you are getting a different type of the trajectory or manifold around the equilibrium point. All these are showing these ones. So you have the tangent space. This is a equilibrium point. If the trajectories are moving towards that, you are getting it as a complete node. And if it is moving away, then it is a unstable nodes, like this thing. So see that. So it is a very good if we have to go in the detail about these ones. These we have studied in one case, rabbit versus sheep. I am not going in much detail, only showing you this one. These are the eigenvalue. If lambda is 3, 2. So this 0, 0 is an unstable manifold because the trajectories are moving away from that. But if lambda is minus 1 and 2, in this case, we are getting that it is a stable node. For this one, minus 3, minus 1, it is coming to be the closure along this one. So again, it is a stable node. For this one, it is coming to be minus 1 plus minus root 2, because minus 1 is a negative value. So you are getting a stable point, sorry, saddle point, because some trajectory are coming closer, but some are moving away from that. So these are the all type of the examples which already we discussed. Here you have all types of the trajectories. Now I will take the one example of a nanofluid. Here we have discussed about that cholesterol deposition in our arteries. So we have used the ferric oxide because our blood also has the ferric component. So we used some magnetic therapy to control those deposition of the cholesterol. So see that this is a red is our blood vessels. Here this yellow is showing the cholesterol depositions. So there are the two types of the trajectories we are using. One is a this one which we have a rectangular coordinates, and this is we are using the cylindrical coordinates. So it is a rectangular cavity and this is a cylindrical cavity we are using it. So based on this, basically this is the work which has been done by the earlier scientists. So we have developed this model by taking this cross sections. So here we have taken the two adiabatic sheets t equal to 0 and t equal to 1. The flow of the blood is this, where this we have introduced this magnetic flux here. So by using, we are using this equations, and these are the condition that when the t equal to 1, so your z is 0, but if t is 0, then z is 1. And stress-free condition, we are using that u, v, w are the velocity component. So del u by del z along this z component are zeros. Then we are using the stream function, that u is nothing but the stream function component, and v is also the negative of that. Means we are using a sort of a Hamiltonian form. And this is the governing equation of the, which are based on the equation of continuity, equation of pressure, equation of temperature, and the one is the important one which where we have used in this third equation, and the second this one as a, this is the main important component where which is showing the magnetic field. And we want to analyze what is the impact of this if we are introducing the magnetic flood by using magnetic therapy. This is this very tough calculation. We are using the non-dimensional quantity. V star is the velocity component, temperature change, then the pressure change, thermal diffusivity. All we have used, and we use the three numbers which are fluid numbers: Prudential number, Rayleigh number, and Hartmann number. Here Hartmann number is based on the magnetic field. So we are controlling this number, how we have to calculate it. These are the different approximation, and we are using the Galerkin approximation for steam and temperature, and using this we try to transform this into the form of the Lorentz system. And lastly, by using all these in terms of the Prudential, Hartmann, and the Reynolds number, we are able to transfer our system into the equation of the form of the Lorentz model. So where all these parameters are given here, and you see that we are using the Jacobian condition determinant trace and calculate the fixed point. Using Rouse-Hurwitz criteria, we try to find out the stability points. And now if the point is 0, 0, we observe that when NT equal to is less than A, we are getting stable asymptotically. For greater than A, it becomes unstable, and NT equal to A is the critical case. Now I'm not going much in detail. I will show you that. Yeah. So now we are using the thermophysical properties of water and the blood and ferric oxide. Now the blood has the density as 997.1, blood has 1050, and the ferric oxide has 5180. Now based on this, we are taking the different cases. When ferric oxide is in the rectangular case is less than equal to 24.4 value, then always you have the stable case. And if the Reynolds number is between 24.5 to 26.1, you have the limit cycle case. But if you have the greater than 26.2, then you have the chaotic phase. Same way, if we are controlling this parameter Hartmann number, which is based on the magnetic flux, if because this is the chaotic case, means if there is no movement of the blood, or there is the much cholesterol deposition, then how to control it? So when R is 28, so if R is 28, this is the chaotic phase. This means if Hartmann number is less than equal to 0.68, you have the chaotic phase. If it is 0.69 to 7.79, we get the limit cycle. But as we are moving the Hartmann number, means the magnetic flux density more than the 0.8, you are getting again the stable spiral phase. So that is the most important part. And you know that the Chinese and the Japanese using the magnetic therapy to control these type of the disease. And see here, Prudential number is 10, Hartmann number is 0.6, and the Reynolds number is 28. So we are getting a chaotic situation. Now what we are doing, we are keeping this as this one and we are controlling this number. Now Reynolds number is 28, but Hartmann number we are changing as we are taking it as 0.7. We are getting a limit cycle form. Now you see that as Hartmann number becomes 1.3, we are getting the regular trajectories. So this is the very good results which we got in case of that, and this paper is published in a Mathematica Applicanda. So which is clearly showing that how we can control easily to the trajectories. So see that as Reynolds number is increasing, so from 20 to 210, you are getting the chaotic situations. But if you reverse it, here Hartmann number is 0.1 up to 0.4, you are having the chaotic situation. But as you are controlling the Hartmann number and increasing that, you are getting a regular and regular one. This means as you are treating with the structure of this one, here we have calculated all DLI, FLI, SALI, and calculating the complete table of these ones. That for value of RA, you are getting stable trajectories because all are negative. Here 1 is positive, so you are getting a critical, means 0, so critical case. Here 1 is positive, so chaotic. Here 2 is positive, but still sum is negative, so hyperchaotic. Here 1 is positive, but still sum is negative, so stays chaotic. Like this, we have analyzed all the structures. Same way, value of HA as we are increasing, all this is 1 positive. So, and the sum is negative, so stays chaotic, 2 positive, sum is negative, hyperchaotic, and then critical, and at last you are getting a stable phase. This is clearly showing that how we have to control that. Complete structures for structure of these ones, and this we have used using the different type of nanomaterials. So it will be the future in case of the nano cooling. We can use these type of the structures in the nuclear reactors, because there we required a cooling should be there to avoid the chaotic situations. And on this, I got the project from National Board of Higher Mathematics, and clearly it is showing that how chaotic situations are under control and giving you the stable system. From this stable to chaotic, and then chaotic to stable system. So I think clearly it is showing that how chaos begins, and it will be very useful in finding the solution at the different observations. So thus in the case of patients with non-uniform cholesterol deposition, so detection of extent of damage with accuracy is easier, as curing through normal drug delivery makes possible to find out the flow of the specific target. Hence, the patient with non-uniform cholesterol deposition has more chance to survive, as chaos occurs for extreme condition, and due to non-uniformity of deposition, narrow space is there which get a stable flow, and using this magnetic therapy. So these are the, I think now time is not there. So I'm skipping these ones, that how body movement is there, and only I'm showing the results. These are the programs here. All these MATLAB codes are there, whatever I have used here. So this is for phase space. This is for Lipno exponent. This is showing how the find out the functions of Lipno. Lastly, now I will say, because we all afraid with the mathematics. So mathematics is not about the number, equations, computations, or algorithm. It is about the understanding. And mathematics is neither pure nor applied. It is a feelings. Once you understand, it never leaves you alone. It is not science, but it is the queen of all sciences. And always I say to everyone, success has only one amazing formula. Stop thinking in terms of limitation. and always start thinking in terms of the possibilities. These are the references. If anyone required that, all the references are there. Thank you for the listening.
Thank you very much, ma'am. Thank you very much, ma'am, for giving your precious time from the busy schedule, or I can say very busy schedule, for this TEW, and providing all the details, in fact, MATLAB codes for the convenience of all the participants. I am really very thankful to you from all the participants also. I hope all the participants have enjoyed this session in a very beautiful or in a very elaborate manner, so that they can use these codes in their research work, as well as to explore this in their academic part also. So, any queries? I hope, ma'am, you explained each and everything in very detail, so there is no query. Because
or maybe they have not understood anything.
No, not at all,
What
sir. Not at all, ma'am. Actually, each and everything is mentioned very clearly in your previous lecture also and in today's lecture also. So they are self-explanatory, and you explained it in very well, in very detail. So as the participants are already saying, thank you, ma'am. So
Thank you very much. And
so with this words, I would like to express my thanks to all the participants, all the faculty members of Mathematics Department, our head of the department, Professor Alka Tripathi ma'am, for her continuous support. We are able to make this event possible. So tomorrow we will connect with the same link at 3 p.m. And thank you once again, ma'am.
thank you very much. And thank you for giving me an opportunity to share my views about these things, because there is a lot of work you can do using these simple tools and techniques. No? So you
Right.
can apply anywhere in your environment, any ecological modeling. So everything is based on the nonlinear modeling, basically. So that is anyone can try, and this is because you're not getting a closed point solution.
Right, ma'am.
So
Right, ma'am.
so you have to find out the numerical approximations.
Right, ma'am.
Thank you once again. Thank you.
Right, ma'am. As I can see, one of the participants had really mentioned in the chat box that it is really very informative lecture.
Thank you. Okay. Thank you very much.
Thank you, ma'am.
Thank you.
Thank you. Thanks to all.